Beneath the hazy orange clouds of Saturn's moon, Titan lies one of the solar system's greatest mysteries. Out there, nearly 1 billion miles from Earth, is a world much like our own, something strangely familiar. But at the same time, it is profoundly alien and utterly unfathomable. For decades, the surface of Titan was hidden from our view, locked behind an impenetrable veil of orange haze that defied our best technology and frustrated generations of scientists. The more we learned about this distant moon, the more tantalizing it became. Every observation raised more questions than answers. Every measurement hinted at something extraordinary lurking beneath those clouds. Until NASA found a way to cut through the haze and reveal the moon's true nature. This is what they found. And it will change everything we thought we knew about life in the universe. Our first close encounter with Titan came in the year 1979, when NASA sent a robotic spacecraft named Pioneer 11 on an ambitious mission to visit the planet Saturn for the first time in human history and investigate the magnificent rings and mysterious moons that surround the gas giant. We've known about Titan's existence for centuries. It was officially discovered back in 1655 by Dutch astronomer Cassini and Huygens, who was using one of the most advanced telescopes of his era. Even from Earth, Titan isn't particularly hard to spot if you have the right equipment. As you can probably tell by the name, Titan is big, really big. It's actually a bit larger than the planet Mercury, making it the second largest moon in our entire solar system. It's 50% wider than our own moon, and roughly 80% more massive. In fact, if Titan were orbiting the Sun instead of Saturn, we'd classify it as a planet in its own right. But despite its impressive size, Titan is still incredibly far away, roughly 886 million miles from Earth at its closest approach. When Pioneer 11 first encountered Titan on September 1, 1979, scientists around the world were eager to finally discover what this massive moon actually looked like up close. They'd been waiting centuries for this moment. Telescopes could only reveal so much. Now, for the first time, humanity would see Titan with its own robotic eyes. But all that the probe was really able to see were the dense orange clouds that completely surrounded the moon. A thick, opaque atmosphere that blocked every attempt at observation. It was utterly impenetrable. No surface features, no terrain details, just an endless, featureless orange sphere hanging in the darkness of space. It was simultaneously one of the most exciting and most frustrating moments in planetary science. However, what Pioneer 11 was able to do, and this turned out to be crucial, was investigate what that mysterious haze was actually made of. The spacecraft carried instruments that could analyze the atmospheric composition without needing to see through it. And those instruments found something very intriguing, something that would captivate scientists for decades to come. A thick atmosphere that was rich in nitrogen, extremely rich, in fact. This is remarkably similar to what we have here on Earth. The majority of our own atmosphere, about 78%, is also nitrogen. This was the first hint that Titan might be more Earth-like than anyone had imagined. But there was another discovery made on Titan during that Pioneer 11 flyby, and this is what really piqued the curiosity of scientists and transformed Titan from just another moon into a high-priority target for future exploration. Hydrocarbons. What are hydrocarbons? Well, the technical answer is that they are molecules made of carbon atoms bonded to hydrogen atoms in various configurations. But here's why that matters. Most of us actually use hydrocarbons almost every day, without really thinking about it. Gasoline for your car? That's hydrocarbons. Propane for your grill? Hydrocarbons. Natural gas heating your home? Also hydrocarbons. On Titan, the atmosphere is filled with methane, which we generally know as natural gas, the same stuff people use for cooking and heating. But Titan's atmosphere contains methane in concentrations that would be explosive here on Earth. It's essentially floating in an atmosphere made partially of rocket fuel. Now, why is this important to NASA scientists? Why would they get excited about finding natural gas on a distant moon? Well, a more practical explanation would be that in addition to being useful as combustible fuel, these carbon-based structures are also known as the fundamental building blocks of life. Important molecules like DNA and proteins, the very machinery that makes life possible, are all built on hydrocarbon foundations. Without carbon and hydrogen bonding together in complex ways, life as we know it simply cannot exist. Here's a more familiar word for you: carbohydrates. Sounds pretty much the same as hydrocarbons, doesn't it? And it is fundamentally the same chemistry. But carbohydrates bring oxygen to the party. They're hydrocarbons that have incorporated oxygen atoms into their structure. So, if we can find oxygen on Titan, then we've got more than just the building blocks of life. We've also got the potential fuel to power that life, to drive the chemical reactions that keep living organisms functioning. And just so you know, right now, there is oxygen on Titan. But we're going to need to go a lot deeper into this story to find it. And when we do, you'll understand why this discovery is so profound. So stick with me. Flying a probe close by Titan also gave us something else valuable: our first accurate measurement of the moon's gravity. And this turned out to be a bit strange, because Titan has a lot less gravitational pull than you'd expect from such a large body. For being so much bigger than our own moon, the force of gravity on Titan is actually a little bit weaker, only about 14% of Earth's gravity, compared to our moon's 16%. This tells us something important. Titan isn't very dense. It can't be made entirely of rock like our moon or Mercury. There must be lighter materials making up a significant portion of its interior. And that opens up some very interesting possibilities about what might exist beneath that icy surface. But here's something fun to consider. The combination of a thick atmosphere and weak gravity creates some unusual conditions on Titan's surface. A person wearing a wingsuit could essentially jump off a cliff and fly like a bird for as long as they wanted. You'd barely need any wings at all. The thick atmosphere would provide so much lift in the weak gravity that human-powered flight would be ridiculously easy. It also makes a flying machine the perfect vehicle for exploring the surface, a fact that will become absolutely critical to our story later when we talk about NASA's plans to return to Titan. But we're getting ahead of ourselves. After Pioneer 11's tantalizing discoveries in 1979, there was a problem. We had to wait. And we had to wait a long time. The technology simply didn't exist yet to send a spacecraft capable of actually seeing through Titan's impenetrable haze. Pioneer 11 had shown us that something extraordinary was hiding beneath those orange clouds, but it couldn't reveal what that something was. It was like being given a wrapped present and being told you couldn't open it for 20 years. During those 2 decades, scientists developed theories about what might exist on Titan's surface. Some thought it might be covered in a global ocean of liquid methane or ethane. Others predicted vast deserts of hydrocarbon sand dunes. A few even speculated about the possibility of cryovolcanoes, ice volcanoes that erupt water instead of lava. But without being able to see the surface, it was all just educated guesswork. The frustration in the scientific community was palpable. Here was potentially one of the most interesting places in the entire solar system, a world that might hold clues to the origin of life itself, and we couldn't see it. We were blind. But technology was advancing. Radar systems were becoming more sophisticated. Computer processing power was increasing exponentially. Materials science was producing lighter, stronger components for spacecraft. Slowly but surely, NASA and the European Space Agency were designing a mission that could finally answer the questions that Pioneer 11 had raised. That mission was called Cassini-Huygens, and it would become one of the most successful planetary exploration missions in history. But before it could reveal Titan's secrets, it had to get there. And that journey would take 7 years. In 2004, after a 7-year journey through the solar system, the Cassini spacecraft arrived at Saturn carrying technology that Pioneer 11's engineers could only have dreamed of. Advanced radar imaging systems and sophisticated infrared sensors. These tools could do what optical cameras couldn't. They could penetrate the haze and see the surface below. The radar worked by sending radio waves down through the atmosphere. These waves could pass through the orange haze as if it weren't even there, bounce off the surface, and return to the spacecraft with information about the terrain below. It was like giving Cassini a form of X-ray vision. When Cassini began its first radar mapping passes over Titan in October 2004, scientists gathered around monitors at NASA's Jet Propulsion Laboratory in California, barely breathing as the first images appeared. What they saw took their breath away. Titan's atmosphere was even denser than they'd expected, 4 times thicker than Earth's at the surface, creating a crushing pressure and rich, complex chemistry. But beneath that thick atmospheric blanket, the surface topography became surprisingly clear and extraordinarily complex. Mountains rising several thousand feet, deep valleys carved by some unknown process, smooth plains that stretched for hundreds of miles, impact craters, though surprisingly few of them, suggesting that Titan's surface was geologically young and active. And something else entirely. Features that looked suspiciously like coastlines. As Cassini continued its mapping mission over the following months, conducting flyby after flyby of Titan, scientists made a discovery that fundamentally changed everything we thought we knew about this moon. Titan has weather. Real, active, dynamic weather systems. But not weather like ours. Not weather like anywhere else we'd ever explored. On Titan, methane, the natural gas we use to heat our homes and cook our food, actually liquefies in the frigid temperatures of -179 degrees Celsius and falls from the sky as rain. Let that sink in for a moment. It rains rocket fuel on Titan. This creates a complete hydrological cycle, just like Earth's water cycle, but using an entirely different substance. Methane evaporates from the surface and forms clouds in the upper atmosphere. Those clouds drift across the landscape. Temperature and pressure changes cause the methane to condense and fall as rain, or, in some regions, as snow. That methane rain doesn't just fall and disappear. It carves channels through the mountains, just like water does on Earth. It flows into rivers that wind through valleys. It pools into lakes and eventually drains into vast seas. Over millions of years, this methane rain has sculpted the landscape into something that would look strangely familiar to anyone standing on Earth. This is a feature found nowhere else in the solar system except Earth. 2 worlds, both with complete liquid cycles actively reshaping their surfaces. Evaporation, precipitation, erosion, deposition, the entire geological cycle playing out on both planets, except one uses water and the other uses explosive gas. The implications were staggering. If Titan has weather patterns and erosion and a liquid cycle, then it must have something else, too. Seasons, climate zones, long-term changes in precipitation patterns. In other words, Titan is a living, breathing, evolving world in ways that no other moon in our solar system can claim. On January 14, 2005, the European Space Agency's Huygens lander separated from the Cassini orbiter and began its descent through Titan's thick atmosphere. This was a historic moment, humanity's first attempt to land on a world in the outer solar system beyond the orbit of Mars. The descent would take 2.5 hours, and every second was crucial. Engineers had designed Huygens to withstand the intense heat of atmospheric entry and the crushing pressure of Titan's dense atmosphere. They'd equipped it with a heat shield, multiple parachutes, and a suite of instruments designed to analyze the atmosphere and photograph the surface during descent. As Huygens plunged into Titan's upper atmosphere at over 13,000 miles per hour, the heat shield glowed red-hot, protecting the delicate instruments inside. At an altitude of about 100 miles, the main parachute deployed, slowing the lander's descent to a gentle drift. And then the cameras turned on. Scientists watching the live data feed at Mission Control saw something extraordinary. Titan's surface gradually resolving from a fuzzy orange blur into clear, detailed terrain. Drainage channels cut deep into mountains, branching networks that looked exactly like river systems on Earth. Dendritic patterns, tree-like structures where smaller channels fed into larger ones, just like the Mississippi River system or the Amazon basin. The evidence was undeniable. Liquid had flowed across Titan's surface in vast quantities, carving these features over millions of years. But where was that liquid now? As Huygens descended lower, drifting through the dense atmosphere, scientists noticed something unexpected. The lander was heading toward what appeared to be a dried-up riverbed, a channel carved into the landscape but currently empty of any liquid. The terrain looked like photographs of dried lake beds in Death Valley or the Australian outback. At 10:38 a.m. Central European Time, Huygens touched down gently on Titan's surface. The landing was perfect, soft enough that the probe survived intact and immediately began transmitting data and images back to Earth via Cassini orbiting overhead. The answer to where all the liquid had gone became immediately clear. They'd landed during what could only be described as a drought. The riverbed was dry, the channels empty. Titan has seasons, long seasons that last for years because Saturn takes 29 Earth years to orbit the Sun, and Huygens had arrived during the dry season in this particular region. The images and data that Huygens sent back from Titan's surface were both familiar and deeply alien at the same time. It was like looking at photographs of Earth, but with everything slightly wrong, as if reality had been tilted just a few degrees off-axis. The rocks scattered around the landing site weren't rocks at all. They were solid water ice, frozen as hard as granite in the extreme cold of -179 degrees Celsius. At these temperatures, water ice doesn't behave like ice on Earth. It doesn't melt or flow. It's as solid and permanent as bedrock, harder than concrete, completely rigid. Think about that for a moment. On Titan, water is a rock. The boulders that litter the landscape, the pebbles that crunch underfoot, the mountains that rise in the distance, all of it is frozen water. As solid and unchanging as the granite formations of Yosemite or the limestone cliffs of Dover. The ground itself was a bizarre mixture of hydrocarbon snow and organic compounds, basically frozen rocket fuel mixed with tar-like substances, with a crispy crust on top. Scientists described it as having the consistency of crème brûlée, or wet sand, with a thin, brittle surface layer. If you stepped on it, your foot would probably break through the crust and sink a few inches into the softer material below. The atmosphere was a thick orange haze at ground level, reducing visibility to just a few hundred feet. The sky wasn't blue. It was a murky, brownish orange, like being inside a permanent dust storm. The sunlight filtering through all those atmospheric layers was dim and diffuse, giving everything a perpetual twilight quality, even at noon. Here was the great paradox of Titan. This moon has abundant water, frozen solid throughout its crust and mantle. But it exists only as ice, harder than rock, and utterly useless for life as we know it. Life needs liquid water to function. Frozen water is just another mineral, as biologically inert as quartz or granite. Or so scientists thought at the time. But Cassini was about to reveal something that would change that assumption completely. As Cassini continued its extended mission over the following years, conducting dozens of radar mapping passes over different regions of Titan, a pattern began to emerge. Liquid on Titan wasn't distributed evenly across the surface. Instead, it was primarily concentrated in one region, the North Polar area. And the scale of what Cassini discovered there was absolutely staggering. Kraken Mare, an ocean of liquid methane and ethane covering more than 400,000 square kilometers, larger than the Caspian Sea, larger than any of the Great Lakes, roughly the size of Japan or California. This wasn't a pond or a small lake. This was a legitimate sea, deep enough to drown mountains, vast enough to have its own weather systems and wave patterns. But Kraken Mare wasn't alone. Cassini identified dozens of other liquid bodies in Titan's North Polar region. Ligeia Mare, the second-largest sea, covering 130,000 square kilometers. Punga Mare, Jingpo Lacus, an entire interconnected system of seas and lakes and channels, all filled not with water, but with liquid natural gas at negative 179 degrees Celsius. The radar imaging was so detailed that scientists could make out individual islands in these seas. They could trace coastlines and identify inlets and peninsulas. They measured the depth of some of these seas using radar reflections. Ligeia Mare appeared to be at least 170 meters deep in places, possibly much deeper in its center. And then Cassini detected something even more remarkable: tides. The liquid levels in these methane seas actually rise and fall over time, caused by Saturn's gravitational pull, just like our moon creates ocean tides on Earth. Titan is so far from Saturn that you might think the gravitational effects would be negligible, but the measurements were clear. The seas of Titan experience measurable tidal forces. This meant the liquid in these seas wasn't stagnant. It was moving, sloshing back and forth, creating currents and waves. It meant that the methane cycle on Titan was even more active and complex than anyone had imagined. Liquid evaporating from these northern seas, forming clouds, blowing south to precipitate as rain in other regions, then flowing through rivers back to the seas. A complete, active, ongoing hydrological cycle. But as amazing as all of these discoveries were, Cassini's most important finding was still to come. And it would come from looking not at the surface, but beneath it. As Cassini's mission extended from years to over a decade, the spacecraft accumulated an enormous amount of data about Titan. Scientists began noticing geological features that shouldn't exist based on their understanding of the moon's composition and temperature. Strange dome-shaped mountains with summit depressions. Smooth, fresh-looking terrain in areas that should have been heavily cratered. Most intriguingly, what appeared to be flow features, lobes of material that seemed to have erupted from central vents and spread across the surface before freezing in place. These features looked suspiciously like volcanoes, but that made no sense. Volcanoes require internal heat and liquid magma, and Titan was far too cold for traditional volcanism. Its interior should have been frozen solid all the way through. Unless... Scientists began considering an alternative explanation. cryovolcanoes, ice volcanoes that don't erupt molten rock, but instead erupt liquid water mixed with other compounds that act as antifreeze. On Titan, that antifreeze would be ammonia. Additional radar observations and gravitational measurements confirmed it. These strange features were indeed cryovolcanoes, occasionally erupting slush, a thick mixture of liquid water and ammonia from somewhere deep within Titan's interior. And that revelation pointed to something even more profound. Beneath Titan's icy crust, below the solid water ice bedrock, there must be a subsurface ocean of liquid water. A global ocean, possibly 100 kilometers deep, kept liquid by the ammonia acting as antifreeze and by the residual heat from Titan's formation and the decay of radioactive elements in its rocky core. Let that sink in for a moment. Titan doesn't have just one liquid system. It has two completely separate liquid systems existing simultaneously. On the surface, seas and lakes of liquid methane and ethane at negative 179 degrees Celsius, actively cycling through the atmosphere as rain and snow. Below the surface, a vast global ocean of liquid water mixed with ammonia, kept liquid despite the extreme cold, occasionally erupting through cracks in the ice crust via cryovolcanoes. And here's why that matters so profoundly. Those two systems can mix. When cryovolcanoes erupt, they bring water from the subsurface ocean up to the surface. That water mixes with the organic hydrocarbon compounds that cover Titan's surface, the same compounds that rain down from the atmosphere. The volcanic activity provides heat and chemical energy. The mixing provides the raw materials, water, hydrocarbons, and various dissolved minerals and compounds from the rocky core. This is the recipe for life. Not complex life like animals or plants, but primitive microbial life, bacteria or archaea that could thrive in this bizarre environment. The fundamental ingredients are all there. Liquid water, below the surface, organic molecules, everywhere, and chemical energy, from the volcanic activity and the interaction between water and hydrocarbons. Scientists have known for decades that life requires three basic things: liquid water, organic compounds, and an energy source. Earth has all three, and that's why life flourished here. But we always assumed these conditions were rare in the universe. Titan proves that assumption wrong. Here's a moon nearly 1 billion miles from the sun, shrouded in a thick haze, with a surface cold enough to freeze methane solid, and yet it has all three requirements for life. The water is hidden beneath the surface. The organic compounds rain from the sky. The energy comes from geological activity and chemical reactions. Titan might not just be capable of supporting life. Based on what we know about how quickly life emerged on Earth after the right conditions appeared, Titan might already harbor living organisms in that subsurface ocean, or in the pockets where water and hydrocarbons mix at the ice-ocean interface. NASA's response to these discoveries was swift and ambitious. The Dragonfly mission, one of the most innovative planetary exploration concepts ever designed. Dragonfly is not a rover. It's not a static lander. It's a nuclear-powered helicopter drone, actually a quadcopter with 8 rotors, designed to fly through Titan's thick atmosphere and explore vast areas of the Moon's surface in ways no previous mission could achieve. Why a helicopter? Remember earlier when we talked about Titan's thick atmosphere and weak gravity making flight incredibly easy? NASA is taking full advantage of that. In Titan's environment, flight isn't just possible. It's actually easier and more efficient than driving a rover across the surface. Dragonfly will be able to hop from location to location, covering hundreds of kilometers during its mission lifetime. It will land in dried riverbeds to sample the hydrocarbon-rich sediments. It will fly to the edges of methane seas to analyze the liquid composition. It will investigate cryovolcanic features to sample the water ammonia slush that erupts from below. Most importantly, it will search for the chemical signatures of life, or at least the prebiotic chemistry that could lead to life. It will look for amino acids, the building blocks of proteins. It will analyze the ratios of different carbon isotopes, which can reveal whether biological processes have been at work. It will study the complex organic molecules that form in Titan's atmosphere and rain down onto the surface. The mission is scheduled to launch in 2028, arrive at Titan in 2034, and operate for at least several years, though possibly much longer if the nuclear power source holds up. The landing site has already been selected: Shangri-La, a large equatorial region covered in organic dunes near the Selk impact crater, where it's believed that liquid water from the subsurface ocean was briefly exposed by the meteorite impact. Dragonfly will carry a mass spectrometer to identify chemical compounds, a gamma-ray and neutron spectrometer to determine surface composition, a geophysics instrument to study Titan's internal structure, and cameras to document everything it sees. This isn't just exploration anymore. This is a hunt, a systematic, methodical search for evidence of life beyond Earth. If life exists anywhere in our solar system other than Earth, if the universe is teeming with biology waiting to be discovered in every corner where the conditions are right, then Titan is humanity's best shot at finding it. Not on Mars, where any ancient life has long since died out, and we're searching for fossils in the dust. Not on Europa, where we'd have to drill through miles of ice to reach the ocean below. But on Titan, where the evidence would be right there on the surface, mixed into the organic-rich sediments, potentially still metabolically active in the pockets where water and hydrocarbons meet. Some scientists believe that if life exists on Titan, it might be fundamentally different from Earth life, perhaps using liquid methane as a solvent instead of water, with completely alien biochemistry. Others think that any life on Titan would be similar to Earth's extremophile bacteria, living in the liquid water ocean below, and perhaps occasionally transported to the surface by cryovolcanic eruptions. Either way, the discovery would be revolutionary. It would prove that life is not unique to Earth, that the universe is capable of generating biology wherever the right conditions exist. It would fundamentally change our understanding of our place in the cosmos. Beneath the orange clouds of Titan lies the answer to humanity's oldest and most profound question. Are we alone in the universe? For decades, those clouds kept their secrets, hiding the truth from our prying eyes and sophisticated instruments. But piece by piece, mission by mission, we've assembled a picture of what exists on this distant moon. And that picture is more extraordinary than anyone imagined when Cassini and Huygens first spotted Titan through his telescope in 1655, a moon with Earth-like weather and seasons, seas of liquid methane, mountains of water ice, rivers that carve through landscapes of organic compounds, and hidden beneath it all, a vast ocean of liquid water where the chemistry of life could be playing out right now. In the darkness beneath the ice, in one of the most unlikely places we ever thought to look. In less than a decade, Dragonfly will arrive at Titan and begin its search. It will fly across alien landscapes, sample exotic materials, and search for the signatures of life in places no human has ever seen. And when it sends back its findings, whatever they may be, we'll finally know whether Earth's story is unique or whether life is a common occurrence throughout the universe, emerging wherever the conditions allow, even in the strangest and most unexpected environments. The answer is waiting for us beneath the haze. And soon, very soon, we'll finally be able to see it clearly.